So start by finding this derivative implicitly. It's still using all the same rules that we've been using. The only difference between this and stuff from the last couple lessons is just that this problem actually includes sine and cosine. But the processes are all the same. Now, as you're working this problem, first hint I want to give you is make sure to note, and this is actually the thing that most people are having trouble noticing on these types of problems, that we actually have product rule that's going to have to be used in order to find these derivatives, because y sine x is really y times sine of x. I'm multiplying those, and so I'll have to use product rule when I find that derivative. On the right side, it's x times cosine of y. So again, I'm going to have to use product rule when I find the derivative of the right side as well. All right, so when we use product rule for this first one on the left side, y times sine of x, remember product rule means find the derivative of one of them, leave the other the same, and then plus, leave the first one the same, and then derivative of the other. So, for this first one then, I'm going to do derivative of y, which is y prime, and then that just is times the sine of x. The sine of x just stays the same. Plus, now this time I flip which one I'm doing the derivative of. So the y stays the same this time, but I now do the derivative of sine of x. Derivative of sine of x is just cosine of x. That's a nice easy one as things go along here. We repeat the process on the right side now. So I'm going to first find the derivative of x and leave cosine the same. So the derivative of x is 1, so that's just cosine of y. Plus, now we flip which one we take the derivative of. So the x stays the same this time, and now I do the derivative of cosine of y. This is actually the tricky part. If something's going to catch you off in this particular problem, this is the piece. Because this cosine of y, it's not cosine of x. It's cosine of y. So notice y, that function of x, is inside the function of cosine. That means chain rule. So I'm going to do the derivative of cosine, which is a negative sign. And that's just of y at the moment. And then that is then multiplied by the inside, which is derivative of y. So that is times y prime. That's the part that probably is going to get you if anything's going to get you. All right, now that we're at this point, proceed from there by solving for y prime. All right, all I did there is I just changed the plus the negative into a minus just to make my next steps a little bit easier and clearer to see. So your first step in solving for y prime means move all the y prime terms to one side. I chose to move them to the left. Doesn't have to be to the left though. And all the non-y prime terms to the right side. Now we can proceed from there, factor the y prime out on that one side where you have them all gathered. And then once you factor that y prime out on the left side, then you have y prime times something. So if I want to know what y prime equals, I divide both sides by that something. And so then that is your final answer for what the derivative equals. So now we have some derivative function that we can actually use to find out what is the derivative in all its different meanings at any given xy coordinate pair. So then up to this point we've found lots of derivative equations like this. Well, today we're going to be adding in one more layer where now this is the same equation. Now that we have that equation, we've already found its derivative. What I'd like to do now is figure out what is the rate of change at this point. So at the point on the curve, pi over 4, comma pi over 4, what is the rate of change? So when I take a look at this problem and I'm thinking about how am I going to approach it, if I'm looking for the rate of change just means derivative. That's what derivative tells us. It's a rate of change dealing with something. So that tells me basically figure out what is the derivative at this point. And so in order to do that, you're just going to take that point, the xy coordinate pair, and plug it in for all of the x's and y's in our derivative equation. And so when we plug in our points for x and y, this is what we're looking at. Now, you will probably end up needing a calculator eventually on this problem, but you don't need one quite yet, I hope at least. Because the cosine of pi over 4, I hope you actually know that one, or can figure it out off the top of your head. That's one of those exact values from the unit circle work. Same thing for sine of pi over 4. It's another one of those values you could know hopefully off the top of your head. And if you do, it's going to make this a lot easier so you don't have to work with nearly as many messy decimals in doing this problem. So pi over 4, remember, that's, if we're talking degrees, that'd be like 45 degrees. That's about where this one's located. And remember, both sine and cosine there are the same. They are both root 2 over 2. And so anywhere where I see cosine of pi over 4 or sine of pi over 4, I can go ahead and replace that now with root 2 over 2. And then once we've done that, then it's a matter of calculating what does this actually equal. But you know, there's actually a way that you can make your life even easier at this point. In fact, there's a few different ways depending on just how far you want to go with it. Because, I mean, we could type this in our calculators right now. Although there is a high probability that we're going to make some sort of a parentheses error because there's so many that go in there with the square roots and the fractions and all that stuff. This fraction can actually simplify before we do any calculations. Do you see how we could simplify it? What do you see in every single term? There is a root 2 over 2 in every single term. So I could actually divide out of both top and bottom to reduce this by the root 2 over 2, which would just be 1 minus pi over 4 over 1 plus pi over 4. That's a lot easier to calculate. A lot less prone to error along the way. Go ahead and calculate that. Figure out what is y prime going to be. Most of us doing this on a graphing calculator, we can just type that in and it can give us a nice reliable answer when we do it because we can actually see what's going in. If you're not using a graphing calculator, there actually is one more step you could have taken with our fraction to make it even easier to type in. Notice I could multiply top and bottom of this fraction by 4. And if I happen to see to do that, I'd have 4 minus pi over 4 plus pi, which is perhaps even easier to deal with. Did you have to do that? No, but just in case you're looking for more little tips and tricks that might make your life easier down the line, you can feel free to do that. Let's check and make sure you did get the right answer out. When you do this calculation, you should be getting something that's about 0.12. All right, and so in doing this, we figured out what y prime was at this point. That is, we figured out what is the rate of change, or what is the slope of the tangent line at that point. Now, because we're actually working with a specific point, and because I do want you aware of these implicit functions and just what they can do, I'm going to blow your mind just a little bit and show you what the graph of this function would look like. It's amazing what an implicit function can do that an explicit function cannot. That can give you a lot of different looks, right? This is all one graph. Now the point that we just worked with, it's hiding down here at pi over 4, pi over 4. So if I zoom in on that point, that's really what we're doing, is we just figured out what was the rate of change right at that point. So that's why it was such a small positive number, because you notice it's increasing slowly at that point. Now, having seen the complexity of that last one, we're going back to some simpler times here. Hopefully you know what the graph of this one would look like already without even having to make the graph. It's a circle. Yep, just x squared plus y squared equals a number. That gives us a circle. So what I'd like you to do, though, is I want you to not just find the derivative, but I want you to actually find the equation of the line tangent to the curve at this point. Now, in working this problem, as soon as you see that word tangent, your mind is hopefully going immediately to derivative. So I already know that in order to find this equation, I'm going to have to start by finding the derivative. And since our equation is written implicitly, that tells me to find the derivative implicitly as well. So, derivative of x squared is 2x. Derivative of y squared. Remember, y is a function of x, so really this is a function within the squared function. So that tells me chain rule. So I do the derivative of the outer function, which is the something squared. So that's 2y. And I do that times the derivative of the inside function, which is y. Derivative of y is y prime. Equals the derivative of the right side. Derivative of 50, derivative of any constant, is 0. Now, we are eventually going to have to be plugging in this point. But notice this actually shows us why we've been solving these for y prime, because I don't want to have to plug that in here and then do a bunch of algebra on it. I'd rather just do the algebra and have a single function that I can use. So solve this equation that we have just found for y prime. So we subtract the 2x from both sides, and we divide both sides by 2y and simplify that result. You should find that y prime here equals negative x over y. A nice simple little equation. Now we have something we can plug into. So now you're going to plug your point into that equation to figure out what is the slope of my line going to be. So you plug in x and y, figure out what that equals. You should find that our slope here equals 1. Yeah, okay, maybe I chose a point that would give us a nice pretty slope. They aren't always so pretty, but certainly makes our next steps a little bit easier, because now that we found the slope, I'm going back to my general equation, y equals mx plus b, and I need to figure out what b is. All right, and so in order to figure out what b is, we plug in for y, m, and x. Strictly speaking, no, you don't have to put in the 1, but I want to make it clear where the 1 went and how it got used. And so then we end up finding that b is negative 10. And now that I know that, I know my equation of the tangent line. Because it has to be y equals 1x, which of course is just x, minus the b, which was 10. Well, plus b, which was negative 10. So we got y equals x minus 10. That's the equation of the tangent line. It's just going to touch this circle right at 5, negative 5. So now another problem where you're writing the equation of the tangent line. Different equation though. Seeing how well we remember some of the subtleties, some of the rules when finding the derivative of something that looks like this. All right, and again, just to give you a little bit of context, check this out. This is what the graph of this particular equation would look like. And you can see there where the point 1, 2 is. So basically what we're doing is we're writing the equation of this line. So it gives you some rough idea about what you might expect. Notice we should end up with a positive slope. And notice it looks like we're going to end up having a y-intercept that's somewhere in the negatives. Although no, I have not drawn this perfectly to scale, so no, you can't just count off the slope there to know. But let's go ahead and start taking a look at how we find this derivative, because there's one area in this derivative that tends to still cause people problems. And it comes up in this problem, and it comes up in a whole bunch of different other areas, including the first one that we did today. And that is that in order to find this derivative, you're going to have to use product rule at some point. Notice right here in the middle, this 2xy. 2x is a function. Y is a completely separate function of x. And so really what you're going to have to do there is you're going to have to treat this as 2x times y and use product rule to find the derivative of that part of it. So when finding this derivative, the derivative of x squared, thankfully that part's still pretty easy. That's just going to be 2x. Plus, now we get into our product rule part. So I'm going to do the derivative of 2x first times y. So the derivative of 2x is just 2. and then the y stays the same, plus, now in this case I'm going to leave the 2x alone and find the derivative of y. And the derivative of y is just y prime. So these two terms come from multiplying that out and using product rule. Then minus the derivative of y squared, which gives me 2y prime, again because it's chain rule, the y function within the squared function, plus the derivative of x, which is 1, equals the derivative of 2, which is 0. And now that you've found your derivative, you can now worry about solving it for y prime. Now, in all these problems in the past that we've happened to do together, it's happened to work out nicely to have the y primes on the left side and the non-y prime terms on the right. But just to mix things up, and because of the signs that happen to work out on this one, I'm going to move my y primes to the right and leave my non-y primes on the left side. But then once we've done that, our process is still the same of factoring the y prime out, where you have the y primes, and then dividing by whatever is being multiplied by the y prime, which gives us this. Now, if you had done it the other way and had your y primes on the left side and moved everything else to the right, you would have ended up there. Which notice is the exact same thing as the previous one that I ended up with, just every single sign is switched. So if every sign on both top and bottom is switched, it's still equivalent to the same thing. Now, one other question that tends to come up at this point is, can I reduce it? Because I see a lot of 2's in there, and I see like the same 2x's or the 2y's. Can I reduce it? And the answer here ends up being no. Because of this 1 in here. This 1 ends up wreaking havoc with any efforts to try to simplify or reduce this fraction. Because remember, if I'm going to reduce it, I would have to be able to divide everything on the top and the bottom by the same thing. And the only thing you can divide 1 by is itself. Now that we've figured out what y prime is, I've figured out the derivative equation. Remember, though, that that was not my whole goal in this problem. My goal is to actually write the equation of the line tangent to the curve at this point. So now that I know the y prime equation, use it with that point to find that equation, please. And so to do that, in order to proceed from here, I need to figure out what m is, the slope, at the point 1, 2, so plug 1 in for x and 2 in for y. And then it's just a matter of figuring out what does that equal. That gives us our slope. Once we find the slope, we can find the rest of the equation. So you should end up finding that the slope is 7/2. Now that I know the slope is 7/2, I can go ahead and plug that into the general y equals mx plus b to figure out what b is. Because I know what y is. Y was 2 equals the slope 7/2 times x, which was 1, plus b. Solve that out. You end up finding that b is a negative 3/2, or negative 1.5, or negative 1.5, however you want to write it. You get a final answer here of y equals 7/2 x minus 3/2, or 1.5, or 1.5, or however you chose to write it.